Good afternoon, everybody. Thanks for being with me today. My name is Petar. I come from Barcelona Supercomputing Center, and today I will talk about some work done in Europe in the field of HPC resilience. The objective of this talk is that you download and read this document. And I have two strategies for this. First one is a hypnosis GIF that I found online and ridiculous color scheme. And if it works for you, that's just great. It's a shortcut. So just download the document, read it, skip the rest of the talk. If the hypnosis GIF did not work for you, surprisingly, I have another strategy. And this is to tell you actually the real story behind this work. And the real story is that indeed we did release the blueprint. It's there, you have a link, you can go download it, please check it. It is a work from numerous resilience experts, 30 of us were working on it. We believe that this document is important, needed, that it was missing, and we find it useful. And on the talk today, I will give you a brief outline of this talk, but more important, I will try to give you a story behind it, to explain you why we did it and why we did the things in the way that we did. The story started somewhere in 2015, 2016. What you see on your screen is part of the call for projects published in October 2015 in the area of HPC in Europe. And the 6-line summary that you see is the expectation of this call from us. So what should we deliver? Summarized in 6 lines. And what you see already in the first line is that we should build a highly resilient HPC platforms. And a bit below, underlined in red, is that designs must respond to critical demands of resilience. Again. So I assume that this is not a surprise for you, because if you check strategic research agendas in Europe in the last decade, they all agree that system resilience is one of the most important exascale challenges. Also, these agendas agree that system resilience is a vertical problem that requires holistic solutions. And if you leave Europe, if you go worldwide, for example, to the US and check the US Department of Energy agendas, you will find the same message. HPC resilience is a vertical problem and it requires holistic solutions. What does it mean? It means that we are dealing with a multi-dimensional problem, that we cannot solve it in one place. So we need to do it in hardware, in system software, in applications, in the way that we think about our algorithms. In the table below, you see various RAS features, such as failure detection, reporting, recovery, redundancy, and so on. And you see a list of components such as CPU, memory, FPGA as a representative of merging accelerators and so on. For each of these system components, there are various resilience features we can think about. And all of them together, so all these features for each of the components should work together to give us something that should be a holistic resilience system. In Europe, we were working in the field of resilience. It's not a new topic that we should cover, so we are not completely in dark. However, if we see the research done in the previous projects, we will see some sparse and unconnected research areas. This is a serious issue because if you have a holistic problem, you cannot solve it with local approaches. Let's make an example of airbag in a car. So if you see the figure below, we have various steps. We have a failure, that would be a car collision. Then we need to detect this collision. And then if we decide that this collision is severe enough, we can activate or deploy an airbag as a way to mitigate the failure. Obviously, I mean, if you have an airbag but you cannot detect your collisions, this system is useless. And you may think that it is a ridiculous example. But yet, if you try to find analogy in HPC projects and prototypes we were building in past, you will find a lot of projects that had some research, very exotic and advanced research. For example, trying to find the optimum gas that would deploy an airbag, but prototypes that at the same time had no way to detect failures whatsoever. Let's make one more parallel between car safety and HPC resilience. In most countries in the world, if you want to use your car in public transport, the car has to comprise some safety features. There is a list of must-have features for the car. Is it resistant glass, safety belts, lights, mirrors, bumpers, so on. It means that if you do not have these features, you cannot use your car. It is not considered to be safe. In HPC, unfortunately, this list doesn't exist. So if we can think about an HPC car and any resilience that this car should include, we can think about the car without glass, without belts, without lights, without mirrors, and no bumpers. And there will be no document that this car would violate. And this is a serious problem. It is so serious that it gathered all the people you see on the screen to think together how we should try to solve it. It is very interesting that most of us in this list actually do work in European projects. And actually we are the ones who are trying to put the label resilient to these projects. We are working in our corners, trying to take care about some very specific resilience aspects. And we're trying to do this well. But at the same time, we accept that by just keeping each of us in his corner, it is unlikely that we will provide resilient HPC systems anytime soon. We agreed about the problem, but what about the solution? If you see this house, it has many problems with the roof, walls, front door, windows. But if I ask you to state what is the fundamental issue, what is the problem that causes everything else, and what is the problem that we should solve first, I hope that you're looking here. And this is something that we are trying to do also in resilience HPC research in Europe. We believe that setting good foundations for any future HPC resilience is the most important thing we should do at this point. And this is not intuitive. This is not just straightforward, doing more of the same we were doing in the past. This is something completely different. We are aware that this will not maybe be considered research. We are aware that this will not bring us top-level publications. But we strongly believe that this is what we have to do. Setting these foundations requires the 3 steps. First, we have to understand the resilience-related characteristics of HPC applications and systems. Some of these characteristics will be obvious for you. Maybe most of them will be obvious. But some of them might be a surprise. Step 2, we have to analyze the resilience features of state-of-the-art HPC systems. And this is not reading the papers. This is not Google Scholar. This is understanding what do we have in the mainstream HPC servers today. Step 3 is once we have this list, and it will be a long list of resilience features that we have today, we have to understand which one of them should have the highest priority to be implemented in European HPC. The outcome of this work is a list of must-have HPC features. Must-have features for something that should be a building block for future European exascale. Just to be clear and explicit, in this document and in these slides, we cover CPU, memory, and FPGAs. This is because the projects who initially funded this effort was focused on this. We are already working on other HPC building blocks, such as interconnect and storage, and we plan to release this data soon. The most important word we should keep in our mind when thinking about resilience-related characteristics of HPC systems is the cost. The cost in euros, dollars, or at least server hours that we have due to the scheduled and unscheduled system repairs, corrected and uncorrected errors, detected and undetected failures. We should also keep in mind the cost of the resilience features that we try to use to mitigate the impact of these repairs, errors, and failures. And then we have to compare the cost of our disease with the cost of the remedy that we propose. I will try to emphasize the importance of thinking in terms of cost with an example that bothers me for some time. The cost of corrected DRAM errors in production is effectively zero. I know that some of you will complain. You can come up with examples where especially a large number of these errors can cause some troubles. But effectively, their cost is zero. The cost of uncorrected DRAM errors is high. For each of them, we have to reboot the server, we have to kill the HPC job, and all the server hours from the beginning of this job or from the last checkpoint are lost. If we see the academia, however, and we see the number of studies that analyze these errors, for each of them that deals with uncorrected DRAM errors, we'll find maybe 10 or 20 of the studies that deal with corrected errors. An obvious question is why. This, for some of us, paradox, however, is obvious only if we think in the terms of cost. And this is why it is important. However, this way of thinking is typically overlooked, and for this reason we emphasize it so much. The second step is understanding the state of the art. But with this, we do not refer to reading the latest scientific papers in this field, but understanding the state of the art in production HPC systems. These features are listed in the documents published by Intel, ARM, and OEMs. And we have to understand them well because they are the gold standard by which the EU HPC resiliency will be measured. As the third step, we should have a clear position about each state-of-the-art resilience feature. Why is this important? Mainstream HPC companies such as Intel, for example, were developing their solution for decades. We cannot pretend that in the first European prototype we will implement all the resilience features that they have. For this reason, it is important to make a clear selection between the features that we must have in our production system at least, from the ones that require cost-benefit analysis, or maybe the ones that are not so essential for now. This is a very complex problem, and I will not enter into the details how we actually did it, but it requires understanding of the HPC RAS requirements, and it again comes down to the cost of the system failures and the corresponding resilience features. And this is the outcome of our work, the list of the must-have HPC resilience features for CPU, memory, and FPGAs. I will give you a minute to go over this list. At this point, you're probably asking yourself, what is so novel about these features and what is the value of this work? And you're right, there is nothing novel about these features. We took them from state-of-the-art documents. But the value of this list is that it has only 11 items. We started with maybe 50 documents with hundreds of CPU, memory, and FPGA resilience features, and we selected only 11 ones that we considered must have. We believe that this list is a great starting point if you're planning to make something that would be a building block for European exascale HPC. It will help you to understand which resilience features you had in mind and maybe to detect the missing ones. Also, it is a great way for reviewers to quantify the resilience of the overall solution. Some of you may argue that the work that I presented is not research. And I agree with you, it's not. At least it's not research we are used to see. However, I hope that we can all agree that it is important, it was missing, and it is useful. It is important because the platforms that lack holistic resilience are not production HPC platforms. They cannot be considered even a building block for a production HPC system. It is missing because the EU-funded research on resilience was scattered and unconnected, and this was not a road towards resilient HPC. For example, we did not even have a document with a list of the must-have resilience features. I spent a lot of effort arguing with some of the people driving European projects on whether or not the error correction codes in memory should be included as a must-have feature in these projects. Now, at least I have a document that confirms my opinion. Finally, it is useful because it helps us to understand where we are in terms of resilience with respect to the state-of-the-art systems and where we should invest our effort. And this is important for the researchers, but also for the policymakers to understand where the fundings should be invested. Finally, a checklist of the resilience features we delivered is very useful for future HPC prototypes, pilots, and production systems. It is important for the people who are planning and deploying these systems from the project proposal level until the final delivery, and also for the people who are reviewing the proposals and deployment of these systems. To summarize, I hope that we all agree that HPC resilience requires holistic solutions. I also hope that we understand that sparse and unconnected research will not bring us these solutions. A good news is that the HPC resilience experts in Europe, together with our colleagues from the US, gathered around this problem and around the general idea. We understood that the first thing we should do is to set some boundaries for any future R&D work in this area. As the first outcome of this work, we have recently published a document that I shamelessly announced at the beginning of this talk, in which we summarize the main ideas toward resilient EU HPC systems in Europe, the first steps in this direction, and the first outcomes. If you have any feedback or comments about the document or about the talk today, please come back to us. If you're listening to this talk, it means that you're part of the community, and we really need your help to keep moving and improve. This talk is recorded for a keynote at the Resilience Workshop held in conjunction with the EuroPAR Conference 2020. The Slack and Zoom Q&A session will follow. If you're watching the video after the conference, be free to contact me over my email. I'll be happy to come back to you. Stay safe, stay resilient.